To present this is actually a paper together with Eduardo Azevedo. We were both grad students with Al, and we thought about different things that evolved to this paper. And okay, so let me just tell you what we're thinking about. So we're trying to analyze large matching markets, thinking about problems like school choice or college admission, where you actually have a lot of students and the market is large, but it's large in a particular sense. So you can make matching markets large in many ways. We were thinking about particular cases where there's many students, but only a few schools. So every school accepts many students. So a college in the US may accept 1,500 students. A university may accept 100 students, or so on. A school may accept a few hundred students. And we thought how can we model this kind of markets? And we ended up using some slightly different model from the regular matching model. And it turned out that it's actually simpler to handle those kind of markets for basically two reasons. One is that we found that we can actually characterize a stable matching instead of as a description of a mapping between students to school and using discrete math, by using cutoffs, like saying for each college there's some threshold for admission. If you're above that, you can get in. That gives us some more like a framework that looks like prices. It's a distinct form, but it looks like prices. And that allows you to work the model in a different way. You can use, instead of combinatorial tools, you can use analysis tools. And this complements with the fact that if we think of really a large number of agents, we can sort of smooth them out and think of a continuum of students. Instead of a large discrete number of students, we can think of a continuum, and they don't really mean that there's an uncountable number of students in the model. I mean that if half a student gets into Yale, that's fine, Okay, I'm not going to do any Yale jokes. I'm being recorded. But okay. So what we get is two nice things. Is that we get a model that on one hand allows for complex preferences. It's the kind of models that we like to do in matching. It's the Gale-Shapley. But in some senses, it will look like the price theory models that you may know from Becker style. Like you can take comparative statics. You can take a parameter of the model and continuously change it and say what will happen to the stable matching. And because the model is continuous and you can describe the stable matching in using tools that look more like analysis, it's actually not too hard to do. So I hope that I'll convince you that this is kind of a useful framework to think about things. So I'll talk about this, and then at the end I'll switch to another kind of example that shows how we actually use this, as well as some applications. So let me sort of start. So this is the way that we usually describe stable matching. We have colleges, they have list of preferences of our students. We have students, they each have preferences of our schools. And it's of course, it's a great model, and you heard so many good things about it. But one thing that it doesn't give you is a direct relation between the parameters of the environment and outcomes. So just looking at this, it's not really clear which student will go where. And if I tell you, well, now I make some students like school 2 better, what will happen? You need to use, you basically would like to run the deferred acceptance algorithm and see what changed. It's kind of hard to see a more direct change. But let's look at a market which has many students. So here I used a slightly different way to plot a market which has 1,000 students and 2 colleges. And basically, again, I'll have to tell you about this market, the same information that I had in the previous slide. What is the preferences of each college over the students? And what are the preferences of the students over the colleges? So this is encoded in this picture in a slightly different way. So each X here, each dot is a student. The preferences are encoded by whether I put the student in the right square or the left square. So this square encodes all the students that have preferences first for college 2 and then for college 1. And all the dots in this square represent students that prefer college 1 and then college 2. So, okay, I told you all the preferences of the students. Now the preferences of the colleges are encoded by scores. So those scores are just ordinals. They're not cardinally meaningful, they're just ordinal numbers representing the preferences of the colleges. And the more to the right you are, the closer you are to a score of 1, the more preferred you are by the college. So this will be a student that is highly preferred by both colleges. There's only a few students that 1 prefers over him, and only a few students that 2 prefers over him. And this is a student that is very unpreferred. What's the opposite? Like disliked by both colleges. This is a student that's very highly ranked by college 1 and very low ranked very low by college 2. And so each one of those dots give me a student. And so basically now I can tell you, okay, so you have all the information now to run the third acceptance. So, sorry, I need to tell you also what are the capacities of both schools. So school 1 has place for 250 seats, school 2 has place for 500 seats, place for 500 students. So now, yes, so now I told you all that you need to know about the economy. So now we can run the third acceptance and see what the outcome is. And this is how the outcome looks in this market. And it's obvious that there's some pattern here, right? So the red axes are the students that are unmatched. The blue circles are the students who are matched to college number 1. And the green squares are the students that are matched to college number 2. And you see that there's a lot of structure here. This doesn't seem sort of random, and it actually sort of like makes sense when I took those lines and drew them. I basically took just a line that separates all the students that got into college 1 from the students who didn't get into college 1. And this ends up to be the same line here and here. And there's a line here as well. And we find that actually every stable matching can be described in that sort of way, because if you got into college 1 and then you can't be worse off than another student who has a higher ranking for college 1 than you and wants to be there. So take any student here that is unmatched. So he would like to be, this student for example, would like to go to college 1. So there can't be any student that is in college 1 that has a lower rank than an unmatched student. Let's take the highest unranked student that has not gotten the unmatched student that is the highest score for college 1. You know that all the students who got in must be above it. Or just taking instead of taking the highest one that got in, let me take the lowest one, the highest one that didn't get in. I can also take the lowest one that did get in, and that basically gives me this line. So I'm by the stable matching, I'm sort of guaranteed to have this structure. And given this structure, it's actually also very simple to describe this picture given those two lines. So we'll consider those two things to be sort of thresholds for admission. If I'm above somebody who got into the school, then I must have an option of going to the school. So that's if I'm more highly ranked than somebody who got to college 1, and then if I like college 1, I should be allowed to go there, otherwise I'll block. So that means that the students in this square, in the top right part of the distribution, can basically choose which college they go to. So you see those go to 1, those go to 2 according to their preferences. Students in those squares can basically get in only to one college, so they go to the one they choose, and those students remain unmatched. So sorry, like this was a question just behind you? Yeah.
Important here that your capacities are less than the number of students.
Yeah, so if I had enough capacity for everybody, everybody will get the first choice. Yeah, yeah.
So this doesn't seem to, you could draw a picture like this no matter how many students there are.
Yeah.
Why do you have a heading when there are many students? If there are only a few students, you should be able to do this.
So when there are many students, the picture just looks nicer. Like it's not, I mean, like it's not, I could follow the same logic, but if there was just one student and I could separate the line would not be sort of I could do the same sort of thing, but
they would still be vertical and horizontal lines.
Okay, so if you find them useful for like any number of students, I'm even happier. I sort of like plotting large number of students. You can see that actually I have.
On the left, it's to the right, but very close to each other.
So if I have many students, you can see that I have 1,000 students, but I can describe using just 2 lines, 2 cutoffs. I can describe the entire like assignment. So per student, I'm using less this number. I don't know. Yeah.
So on this cutoff, so the ratio, for example, red one to blue one, that depends on the capacity.
Yeah. Yeah. So the number of blue dots here is 250. Yeah? If it's not, then one of the x's would block. One of the unmatched students would.
Depending on the capacity.
Yeah, and I'll be more precise about. I should say I just foreshadowing like things we'll do more precisely in a bit. But I just want to sort of like give some sort of the intuition that we worked with. Yeah.
Is it true that total number of blue dots on 2 graphs is equal to 200?
Yeah, the total number of blue dots is 250 on both of them together.
Because these are different.
Yeah. So those are students with different preferences, but they take the same. Each one of them takes a seat. Yeah. Yeah. So that's basically what I described now. Like I can say this is a threshold P1 and P2 for admission, and I can just look at sort of the demand, those cutoffs. So I said that those students must demand their first choice. Those students demand their first choice. Those students demand basically the only school they can get into. Same here. And if I now that something that I can use if I have many students, that I sort of know just from this cutoff how many students fall in this range. If I have a distribution, I can just calculate how many students will fall here, and then sort of generate something that looks like a demand. If I say if cutoffs will be here, then this many students will have to be assigned to each one of the schools.
You know that if there's no aggregate uncertainty.
Yes, there's no, yes. And then I can write down sort of like a supply and demand condition that must hold if I have a stable assignment. Yes?
A cutoff with 2 graphs the same?
You mean this P2 and this P2? Yeah, they're the same. And the same P1 here and here. Huh? Yeah.
Did you see there are equal numbers in both boxes?
No, like I think it turns out in here that we put equal numbers in both boxes, but it's not necessary. You can definitely have like that this preference is twice more likely than the other, or any distribution of preferences that you like. Yes.
So the scores at colleges, did you draw them randomly from any distribution, or?
So in this example, yes, but you can do any distribution. I'll define everything and go through the math. So if you
It keeps working, like you've tried different ones.
So if you have questions about the model, let me show you the model. This is just the motivation. Yeah? Okay, so basically we do 2 things. One is that we use sort of a supply and demand kind of framework. I told you that instead of using the stable matching, I can just look at this kind of thresholds and I get a demand equation. So I'll be very precise about that, but it turns out to be completely equivalent to stable matching. Instead of running the first acceptance, I can say what are the P1 and T2 such that when I tell the student those are the thresholds, demand your school, I get that demand clears the demand of schools clears the market. The number of students that go to each one of the colleges actually is equal to its capacity. And second, now there is something that a large number of students does buy me, which is that those things, if I move them a bit, will vary the number of students that would like to go to each one of the schools continuously. So instead of having this kind of curve, which is jagged, I have a discrete demand. As I change the threshold, I have another college student or not another student. I sort of look at a continuum of students, and then I sort of like take a fraction of a student and can move them between schools. And this is just, it's not meant that we really move fractions of students between schools, but it helps us do the math in a much easier way. And there's some technicalities that come from working with continuum. I would think about them as technical constraints. Like I really do mean to think of a large number of students. So when I think of problem of measurability or stuff like that, I just want to figure out what is the right definition to get me to what I'm aiming at, a large number of students, without falling into all sort of like problems of measure theory. So let me give you the model itself. Yeah? So we describe the economy by a set of colleges. For each college there's a capacity, and the capacity is a real number. You can get a continuous amount of students. And student types encode basically all the other information in the environment about preferences. So student is a collection of two items. One is a strict preference over colleges, and that's basically what we always have about students. The other part is encoding the preferences of colleges over the student. This is your location in the square that I had, and we encode it as a score. So for every college C, you get a score from 0 to 1. 1 is the most preferred student, 0 is the least preferred student, and this is just an ordinal number. It doesn't have any cardinal meaning, like half is not twice as preferred than quarter, but just if you're higher, then you're more preferred. Again, we're matching, we just have ordinal preferences over students. And I should say also that preferences are responsive in all this model. This is an common underlying assumption. And using those two things together, once I know the scores of all the students and the preference of all the students, I have all the information that I need in the economy. And now I don't tell you how many students are of each type. I create a distribution over the students. So if you want to have a distribution over the students that has uncorrelated preferences between the two schools, then you'll just draw the students with those two components drawn, preferences drawn IAD, either 1, 2 or 2, 1. And this is just drawn uniformly out of the square, 0, 1 squared. If you want to have correlated preferences over students, those scores will have equal components. So if my score at EC at E1 will be exactly equal to E2, that will give me perfectly correlated preferences between the schools. Yes?
So you have a responsive preference for the school, right?
Yes.
So is that necessary, or you can pass through a function which
So we use responsiveness quite a lot. Yeah? And so holding responsive preferences, then the only the restriction that we make on what the economy looks like is that basically preferences are strict, which in the discrete model says there's no two students that have the same priority in every college. Here it would say that there's no positive mass of students that has the same priority in a college. So formally we say that by the mass of students, theta in the space of all students, such that the score at some college is exactly equal to x, is 0. So when I look at a particular score, I can always, it's a zero measure, like there's no positive mass that I would like to admit altogether. But it just says that all the positive mass of students is sort of continuously spread across the different schools. Okay. So let me redo the example that I showed you before, just in its continuous version. So now I have those two squares, and now I really draw a uniform distribution. So now instead of small dots, I have continuous dots all over the space. And now let me switch to this. So now I have those two preferences, and now let me run the third acceptance with it. What? What do you mean? So it means that if I take a particular score, what is the mass of students whose score for college 1 is exactly half? So that says that if I look at the mass on this line, on the vertical line, the color here and here, the mass of students whose score is exactly half, it's 0. So it basically says that if I adjust my threshold slightly, I can always match my capacity. Like the... Yeah, I don't have atoms. It's perfectly fine if like the diagonal has all the mass. So it doesn't have to be a continuous with positive density over the entire square. It's just that when I cut over every line, the measure is 0 over every vertical line. So let me run the third acceptance with this economy. So the algorithm. So in the first round, we run the third acceptance in the same way we do with the discrete model. Every student will propose to his first choice. So now in the blue, there are students who propose to the school 1. In red, there are students who propose to school 2. So now all the students in this square have 1 as their first choice. They all propose to school 1. All the students in this square have 2 as their first choice. They all propose to 2. So now the capacities for the schools were adjusted proportionally as I had before. Before I had 250 seats for over 1,000 students for school 1. So now I would say that the capacity for school 1 is a quarter of the mass of students can get in. And for school 2, I had a capacity of 500 out of 1,000. So normalizing, it will have a capacity of half. So that means that school 2 now is fine. There's a mass of half that apply to it. And there's a mass of half that can be at the school. So nobody will get ejected. But school 1 now is over its capacity. So it needs to eject a mass of quarter of students. And it will eject the lowest ranked students according to its preferences. He prefers students that are more to the right. That's the domain where we plotted that score. So we will eject those students. The lowest ranked mass according to his score. So now all those students were ejected. In the second stage, they apply. So they apply now to their second choice. They apply to school 2. Now school 2 is over-demanded. I'm using schools and colleges interchangeably. I apologize for that. So college 2 now is over-demanded. Now he has to eject the lowest ranked students according to its preferences. So those are the lowest ranked students according to his score. Those are the ones at the bottom. So all those students will get ejected, both squares. So those students now just got ejected from all the schools. They're done. Those students can now apply to their second choice, which is school 1. So you have them apply to school 1. Now school 1 is over-demanded. So it will eject some students, again, increasing taking only students that are more to the right, rejecting those students that are the lowest rank according to its preferences, and the total mass of those two squares is now a quarter. That's how we decide on how much to reject. And now those students will apply to the second choice, and so on. And eventually we converge to this thing. Well, you get the same structure that we had before. And I should say, this never finishes in finite time, but this process clearly converges because the mass of rejected students becomes smaller and smaller with every step. If I just let it run for infinite amount of time, I'll get here. So, and that's very quick on the laptop. Okay, so I got the same structure, and now I have those thresholds. So now let me go back to my theory, like to the theory, and tell you something about those thresholds now in the continuum. So actually, I should be defining a matching before I do this, but sort of intuitively, I sort of assume that we have a matching, but like that's the definition we have for stable matching, and it's basically what you sort of assume given what given the model. Like now that I have a continuum of students, I have a mapping from this set, the continuum, to either a college or being unmatched. And every college is now matched to a subset of students. So everything here is completely standard, except for the last technical restriction, which is meant to deal with zero measure of students. So if I wouldn't have this restriction, then I can always add a zero measure of students to a college. And I don't want to deal with that. I want to sort of have a continuous change in the number of students, but I want to have the stable matching fixed and not determined only up to a zero measure, so I just impose right continuity, saying that if you admit a student, the students that are slightly to his right must also get in. And then we adapt the definition of stable matching, saying that blocking is, again, the same kind of phenomena. We look at the same kind of definition, just adapted the continuum. We look at a point-wise definition. Even though we have a continuum, we think of a particular student and a particular college. And it's enough to have one point, one student who is blocking. So a blocking pair will be one student, one point in the continuum, that prefers the college over his match, and the college either didn't fill its quota, sort of strictly, there's strictly extra mass at the college, and that's where I actually need to do the zero measure, like deal with a bit with zero measure. I can't say it's weakly, I can't say that the college is at capacity. I can't say that the student can't get in without violating the capacity, because I can always add another point without violating capacity. It's a zero measure event. But together with the right continuity that I had before, it would say that you can't actually move one point. If you move a point, you have to move a neighborhood of students. So anyway, so it turns out that basically it still works out the same way. And now I just sort of say the student didn't fill its capacity in mass instead of discrete students. And the other option is there's some other student, again, just a point, just one point in the square where the student is matched but is less preferred. So both of those will give me a blocking pair. Okay, so stable matching has basically the same definition again. Slight adjustment for the fact that we have a continuum, but nothing to actually worry about. And now that's sort of like defines the stable matching. What I did before running the deferred acceptance should come up to a stable matching at the end. but let me define now the what I said about cutoffs, about the thresholds. So I'm going to call a cutoff, a vector of cutoffs, a vector of just coordinates between 0 and 1 when I say that a cutoff PC is sort of a minimal score required to get into a college C. So think of this as sort of like minimal SAT scores. If you have above, I know, 1750 SATs, then you can get into the college, otherwise you can't. And it doesn't mean that you have to go, it means that it's your option to go if you're a student. It's sort of like a price. So the demand of a student theta given prices P will be the most preferred college according to his preferences, such that his score for the college is above the threshold. And it will be useful to look at aggregate demand, which is just the mass of students that demand every college. So given the cutoff P, now I can look at a procedure where I take every student and I tell him, point to your favorite school. So you know your scores. So you know you have 750 SAT and your, I know, LSAT, like nobody has LSAT, and your MCAT is a number, your sort of like GMAT is a number, and so on. For each one of those, for each one of the schools, you know, according to your scores, whether you can get in or not. So select the college that you like best out of like the ones that you can get into. And that will get me this d theta of P. And now I go over all the students and ask, given the thresholds, how many students will actually point or choose school C? And I denote this by DCP, the demand for college C given cutoffs P. And this is just the measure of all the students that demand the school C. So now, given this demand, do I get a stable matching or not? So each college is pointing to a school. I can say each student is going to that school. This is going to be right continuous and all the other things that are required out of matching, except that I may send more schools to a college than the capacity will allow. So if I set this threshold for every college in the previous example, everybody will decide to point to his most favorite college. So I'm not necessarily going to respect capacities. And vice versa, on the opposite, if I set the cutoffs too high, maybe nobody can get in anywhere and everybody is unmatched. So what does it mean for a cutoff to be sort of like creating a sensible matching? It must clear the market. It must allocate the right number of students to each college, meaning that the number of students that demand college C, given the cutoffs P star, must be below SC, below its capacity. And if the cutoff is positive, meaning that there's some low-ranked students that didn't get in, and remember that it's a continuum, so there's always going to be a student that has a rank epsilon between any positive number and 0. If there's some students that didn't get in, the college must be full. So if I have a positive cutoff, this must hold with equality.
That's because you are assuming that all students are acceptable.
Yes, sorry, I didn't say that, but we're assuming that all students are acceptable. This is just for notation simplicity. It's not, you can just add dummies and get rid of it. No? So if, yes?
So, like, you use the SAT scores as examples of cutoffs. So, but in the graph, your college 1 and college 2 have different preferences of students. Students can have high scores in one college and low scores in another college.
Yeah. So the way that I'll represent two colleges having the same preferences is just putting all the mass of students on the diagonal. So it may be that according the description of the economy, whether things are correlated or not, is how many students are there that have a very low score for one college and a high score for another. If all students use SAT, the measure is 0. And all the measure will be concentrated on the set of students that have the same score at every college. Yeah? That would be the diagonal in those boxes. Yeah, the diagonal is perfectly fine. It's only that, yeah, the diagonal can have a positive mass. It's perfectly fine. Yeah. Of the what? No, sorry, I'm not sure. Okay.
What was the question?
What? Sorry,
I can't hear the question.
The name of the article of the
I think it's his book. I think it's not the article. No. Yeah. The 7th. Okay. Yeah. Okay. So why are we introducing those cutoffs? So we want to relate those cutoffs to stable matching, just like the intuition that I gave in the before when I had this picture with the dots, that we saw some pattern, like those dots were organized into squares. We saw the same thing when we did the continuum, and we found that we can organize the squares using those lines, those thresholds. So let's formalize this relationship. So given a stable matching, I can define a set of cutoffs by looking at the lowest rank of accepted students in each one of the colleges. So I can say the threshold for college C is simply the minimal rank, the minimal score of every student, of all the among all the students that got into the college.
This is assuming you say stable, do you mean the students are choosing?
Yeah,
The
it's
student option.
it doesn't any stable matching. I'm not
Even if it's college.
college proposing. It's just I'm just using the stability, no blocking pairs property. So the lowest score out of all the colleges that got in, that will generate some number that I'll call a threshold. If I have thresholds, I said, like we have this point to your favorite school process. So this process generates a matching, and if it's a market clearing cutoff, we said that the matching will be valid because the amount of students that point to each school, it's exactly its capacity or less. So that will create a matching. So I'll denote mu, the matching that results from doing this proposing procedure given cutoffs P. Just every student will be matched to the school he demands given those market clearing cutoffs. And now I have this lemma that is basically the reason that I sort of like drew this line, is that both of those operators are actually translating equivalent objects. So market clearing cutoffs and stable matching are actually exactly the same thing, just represented in a different way. And we can represent stable matchings equivalently by looking at market clearing cutoffs. So let me go back to the example. So we said, okay, we ran Gale-Shapley at the end. I didn't tell you yes, but in a slide, it does converge to stable matching. So this is stable, and it's basically stable for the same reasons. And nothing substantial changes except that now I need to prove that it's stable with respect to when there's a continuum of students, but the proof is actually exactly the same. And now I want to ask, okay, given that I got that this is stable, I can still see that there's some sort of like threshold structure here. So let me write it down as cutoffs. And now given this lemma, I know that it's looking at the set of stable matching is exactly equivalent to looking at the set of stable of market clearing cutoffs. So I can write equations. Market clearing cutoffs are described by the supply and demand equation. It's just saying that I write a cutoff P1 and P2. And those cutoffs induce a demand that exactly fills both schools. So assuming that both cutoffs are positive, then the demand for school 1, which is the area of this plus area of this plus area of this, and the area is measured according to my eta, distribution over student types, which is uniform, so I just take the area here. The total mass of those two squares must be equal to the capacity of school 1. So this is just a calculation of what is the total mass of those three squares. So its width is 1 minus p, and its length of those three together is, all of this is 1 plus p2. So over together I get 1 minus p1 times 1 plus p2, and the density in each point of the square is half, so I divide by 2. And I have same kind of equations for school 2. The total mass of the three red parts here must be equal to Q2. And now this is just like simple algebraic equations. I can plug in the number and get that P1 must be equal to this number, P2 must be equal to this number, which turns out to be exactly the same as what the deferred acceptance converged to. And by the cutoff lemma, this is not a constant. This must also always happen. If I have a stable matching, I can always calculate the stable matching by just taking the cutoffs. And now I got two things. One is that instead of running deferred acceptance, I could solve for what is a stable matching by just solving two very simple equations. Second, those two simple equations have a unique solution. So now I know that not only this is the stable matching that came out of the deferred acceptance, it's the unique stable matching. Okay. So this actually is a pretty powerful tool because it's very easy to work with cutoffs in a lot of things. Cutoffs are characterized by a set of simple equations. I can solve things using the equations and then sort of take them back to stable matching and say, what does it mean for the stable matching? So just to start up and say, like, the continuum model is sort of, you take in a continuum of stone, it doesn't really change most of the results that you're used to. So the deferred acceptance work, it converges to stable matching. The stable matching always exists, and the set of stable matchings is a lattice. The set of market clearing cutoff is also a lattice, and the correspondence between stable matchings and cutoffs also preserves the lattice structure. And the rule hospital theorem also still works. So the mass of students that are matched to each college is constant across stable matching. And one thing that is useful in this is that the amount of unmet students in each stable matching is fixed. So that gives us some sort of like nice properties that we can use to prove things. And now let me give you sort of a new sort of like theorem that we can prove using those kind of properties and the continuum structure, that sort of says that the fact that I found a unique stable matching in the previous example is actually not exceptional. It's actually what always happens in this continuum model. So if we have two different conditions, one is if eta, this distribution of students, has full support, meaning there's a positive probability to be anywhere in the square for any kind of type of students, then there is a unique stable matching. And suppose you don't have a full support, suppose you have a different distribution, then with a technical condition that the demand should be continuous and differentiable, then for almost every set of capacities S, you have a unique stable matching. So this is saying that it's not impossible to write an example here where you have a non-unique stable matching, but it has to be a knife edge case. So if I take your example where you don't have a unique stable matching of the continuum and I just adjust the capacities by just a tiny bit, I always get uniqueness. Sort of saying uniqueness is sort of the norm in this model. Yes?
From the independent conditions for unique stable matching.
Yes.
Do you have any weaker condition for the to guarantee the just stable matching? Or is
Stable matching always exists. A stable matching
overall
always.
condition,
What?
regardless any condition?
Regardless, like basically just the assumption that I had in the beginning that you have strict preferences.
Then,
Yeah.
The condition that D is continuously differentiable, though, is kind of a little far from the. To
Yeah.
verify that, a little far from the primitives.
Yes.
Of the,
Yeah. So if you have, if this distribution has a density, for example, that would be a nicer condition to say, but it's actually sometimes we don't want eta to have a density because we want all the mass to be concentrated on the diagonal. So yeah, it's not a condition on primitives, but it's the simplest way we find to say what we mean by this condition, with this condition on primitives. So let me go quickly through the proof of like this of this first. Actually, maybe I can do both. Let me go quickly through the first. So let's assume that there are two different stable matchings. So given the cutoff lemma, I can equivalently think of two different market clearing cutoffs. And for simplicity, like the proof is a bit more general, but for simplicity, let me just consider now, well, one of them is strictly lower than the other in both cutoffs. Like I can have that one of them is different only in one dimension, but let's think that I have two colleges and P plus is bigger in both dimensions. So what will happen under each one of the different cutoffs? Well, if you're below this cutoff, those thresholds, then you'll be unmatched. So the set of unmatched students under the cutoff P minus, the lower cutoffs, is this one. Under the bigger cutoff, the set will be now the shaded bluish area, including covering the red square. And now I know from the rural hospital theorem that the total mass of unmatched students must be the same across the two different stable matchings or the two different market clearing cutoffs. But that necessitates that this bluish area must have a measure 0, must have no students in it. But that cannot be if I have a positive density, if I have full support. So that's it. That's the proof. Like you must have your unique stable matching. The proof for yes.
Then you compare if you are to assume two stable cutoffs, shouldn't you assume like this one is this okay. Never mind.
Is it okay? Yeah.
Never mind, yeah.
Okay. Yeah.
It's impossible that you have two different stable matchings where everyone is matched.
Two different stable matching where everyone is matched.
Yes, in both of them. Is it possible?
So let me like it is, but if you have two different cutoffs and one of them is bigger than other, you'll get this. And if whenever sorry, you're right, because I skipped a step when I did this. Because if you have two different stable matchings, I also need to use the lattice theorem here. I jumped a step, sorry. Because if you have more than one stable matching, then you must have a smallest one and the biggest one from the lattice structure. Yeah? So right, there can be multiple stable matching, but by the lattice structure, I can always get the lowest one and the biggest one, and then I always get something like this picture. If you have something different,
Here you assume that actually there's more students than seats in the colleges.
yeah,
You always have some animation. But suppose that they're equal, so you always have all the students matched.
yeah.
Then is it possible that both your points are in the bottom left? But how can you infer them then that
So the rule hospital theorem sort of also tells you can also prove that if a college did not fill its capacity, it must be matched to the same set of students in every stable matching.
This is asking when
Yeah.
all colleges.
you have exact quota, so everyone is matched? Yes, and
No, but the first was
So I think,
zero cutoff. Occasionally you have zero cutoff.
so if I have a cutoff of 0, you mean I have then and they're unique, or I'm not sure what you're asking, because
Okay, we will talk later.
okay, so ask me like yeah.
That zero in one dimension, but positive in the other, or the other
Yeah.
is reversed.
yeah,
They're not-
took it.
One is not large in both dimensions. but-
So this is just a simplified version of the proof, but like that works still. Like okay. No? You may need some dummy if you want to represent this. You may need to add some dummy students at the bottom to represent students that are matched. But it should still work. Yeah. So the second case is what happens when you don't have full support. And things still work for basically the same reason, but we need to use some analysis theorems. So South theorem says that if you look at the points where a function is not differentiable, so at the sort of y value, at the mapping on the so I have here a correspondence, and then I sort of like look at the function and I sort of try to cut it where it's not differentiable. So the set of points here, there's a set of points where the function is not differentiable, but they map just to one point here. So the set of values that they take on the sort of y-axis, it's kind of flipped here, is of a measure 0. Which kind of says, in sort of like intuitively, it should say it's irrelevant that you have a non-differentiability in your function. So, what does it mean to have two market clearing cutoffs in general? It means that in this point, demand is the same as it is in this point. So total demand for the total colleges. But in the middle, I change something about the relative prices, the relative thresholds of the colleges, and still total demand must stay the same. So this is something that sort of creates non-differentiability, and in the continuum, we can sort of say this is not generic. This is something special must happen. When I adjust the cutoff for one college and exactly adjust it enough for the other college, the students just exactly switch. This seems like something here. There's some sort of like condition that must be exactly satisfied, and this is not generic.
When there is no mass in the square,
Yeah. So you need.
the probability is zero.
So you need no mass in the square, and you need that the sort of like the it comes out that demand has a singular derivative here, which would say that its values, its capacities that it will get is sort of a non-generic value. If I tweak a bit the capacity for the students, for the schools, either I'll have slightly excess demand now in each one of the colleges, and then I'll collapse to the student like favorite, or if I reduce the capacity of one of the colleges by a bit, I'll collapse to the school favorite out of the two. So now I want to tell you also that of this we get some like uniqueness results. We get some other ways to prove things, but how does this correspond to the old discrete model that we have? So we can actually define the discrete model using the same language, only that if I talk about the discrete model, the measure must be atomic. Just a set of finite students, I can think about it as a set of atoms in the space, each of them equally weighted. And the cutoff lemma will still hold in the same way, just like you wanted it to, except that now when I have a cutoff, it's not going to be unique, because if, let's say, I put students on the grid, and students have a score that is 1 over n, a multiple of 1 over n, now I can take any cutoff between 1 over k over n, k plus 1 over n to differentiate, like to cut the student, the lowest student got in from the highest student that didn't get in. So in the continuum, there's only one point to slice, but in the discrete, there's many points to slice in the middle, so I don't get exactly this correspondence which translates exactly stable matching and market clearing cutoff. There may be multiple cutoffs that correspond to the same stable matching, but it's a multiplicity that's sort of technical. It's not that those different cutoffs are differently in a meaningful way, they're just that I don't have a way to pin down what is the right place to slice between k and k plus 1. So one of the combination of the operators will still give me the identity, the other will not necessarily. I can't get back to the same cutoff that I started from. And now I want to ask, what is the relation between the finite economies and the continuum economies? So, and especially I want to know, I set up a continuum model, does it really make sense if I take a model with a large number of students instead of a continuum of students? Will it correspond to the same thing? Otherwise, what does the continuum mean, right? I'm not interested in the continuum by itself, I'm interested in it as a representation of a market with a large number of students. So we think of convergence in this model. What does it mean for me to approximate some economy? So a sequence of economies converges to an economy if the distribution of students converges in reconvergence sets. This is just the topology that you use for that you want to use for convergence measure. That basically means that for any set of students, the measure of the set must converge. And the capacity is when those schools converge. This is just convergence in Rn. Matchings, to say which matchings will converge to a matching in the end, it's much easier to look at the corresponding cutoffs. Because when I talk about matching, it's functions from the set of students to the set of colleges. This is a pretty high-dimensional object. But when I know that I can actually correspond each one of them to a vector in Rn, I can just translate this to convergence in Rn. So a set of colleges will converge if the relative cutoffs converge. And last, I can ask what is the measure of multiplicity here. And the measure of multiplicity can be taken by how far the different cutoffs are. For if I have two different stable matchings, then saying how different they are can be measured by taking the corresponding market clearing cutoffs and saying how different are the market clearing cutoffs in the metric of Rn. So now I defined what does it mean to converge, what does it mean for the stable matching converge, and how much multiplicity we have. What is the difference between two different stable matchings, and what is the maximal difference between two stable matchings, the diameter. So now I want to ask whether when I take finite economies that look more and more like the continuum economy, will I get stable matching that looks similar? And the answer is yes, if I have uniqueness in the limit. So in the example that I started with, I had this continuum economy with a uniform distribution of all students. And before that, I showed you what the discrete one looks like, and they looked pretty similar. And this will hold because when I have a unique stable matching, I know that any sequence of finite economies that in this that the distribution of our students and the capacities converge to a limit economy that has a unique stable matching will give me a sequence of stable matchings that converge to the limit stable matching. And this is basically upper Hermite continuity if I have a set of stable matching for the continuum economies. The limit will give me a stable matching for the limit economy, and if there's a unique stable matching at the limit economy, this must be the one that this must be this mu one. And it's also the condition that I have a unique stable matching is necessary here, but we said before that this is actually the common case. When we set up a continuum economy, generically we should have a unique stable matching, so generically we will have this convergence. And more than that, we get that the diameter is actually converging to zero, so as the finite economies become bigger or closer to the continuum, they get an essentially unique stable matching. So I showed you that there's a unique stable matching in the continuum in the limit. You can take it to this, that if you have a large economy, a college with 1,500 students, you expect that it may not have a unique stable matching, but it will have a set of stable matchings that are all very close to each other, so essentially unique. And last, the stable matching correspondence is continuous at this economy. So this is also thinking not just about convergence of discrete economies to continuous ones, but saying, what happens if I take my continuum economy and change it a bit? Well, the stable matching will change by a bit, as long as you have a unique stable matching. This is useful if you want to work with changing the stable matching continuously. You want to sort of tweak some parameters of the environment, or if you sort of doing something econometrically or something, estimating parameters, and you got some stable matching and you say, well, I'm not really sure that I got the parameters exactly correct. Will things drastically change when I slightly change the parameters? And the answer, if you have a unique stable matching, no. Stable matching actually sort of behave quite smoothly with the underlying parameters. So what do we do with this? So one question that we can ask is ask a question of what is the incentives to invest. So this is something that would be challenging to address in a regular framework of stable matching. What will happen if I change the environment, if I change the preference of the students? And this is a question in the labor literature. Hatfield et al. Made a pretty sophisticated model that tries to address it in the mentioned literature, but even in their model, they could say something, can it help or can't it help? It's very hard to quantify things if you look at a discrete model of stable matching, saying, suppose I rank you higher, what does it, how can I sort of like adjust this by a parameter or something, saying you invested something in ranking you higher, how can I measure sort of a return, a cost investment versus returns to different things? And a lot of the time we want to quantify things. So here, given that we have this model and things are very tractable, we can actually do this quantification. So I'm not going to go through this in enough details to go through the entire model, but let me just sketch a bit. Think of continuum economy where the ranking of a student depends on some delta, some vector of qualities of schools. So the scores of the students are distributed regardless of this delta. and there's a continuum of students and continuum distribution. But the preference of a student depend on something that the schools can decide on. And you can think of having a cost function. A school can invest in having better teachers, having better delta, and your utility is sort of monotone, increasing in this parameter, in how much the school invested to be better. And given how much schools invest in their capacity, there's going to be a distribution that depends on the investment of how many students like every school. And we can write down what will be the average quality of the incoming class, which seems like a messy expression, but it's actually not. It's actually, when I read it, I hope it will be simpler. The average quality of the incoming students is just taking the integral over the match that the set of students that the college is matched to, and everything is parameterized by delta because it depends on how much the college and other college invested. And what are those scores? It's just the score of the student at the college averaged according to the distribution of preferences. And this is an object that we can calculate. It's not actually that hard to calculate it given the primitives of the environment, because what we'll do is we'll just take a given distribution. Given distribution will give us the market clearing conditions. For the market clearing condition, we'll just calculate cutoffs, and then the cutoffs will get this integral into some tractable expression. So we do this in the paper, and we can show that it's tractable. For now, let me just show you that we can do I forgot what it's called. When you take derivatives of stuff. Comparative statics. Yeah, sorry, I'm blanking. Okay, so we can do comparative statics. Sort of asking, how will your quality change if you change your investment in your quality? And there's a lot of expressions here, which I don't intend to get into. But there's some direct effect saying now most students like you, so you get better students. That's a direct effect. And like the students that are highly ranked and like you. But there's also an indirect effect that the students who disliked you before will now go to you, now don't go to other colleges. So going to other colleges is, like, for students to go to other colleges is actually good for you, because if students that you don't like go to other colleges, they will reject other students from that college, which may apply to you. So if others, in other words, if other schools have to become more restrictive, then if it's harder to get into the other schools, more students will apply to you. Like if Harvard will cut its class to half its size, a lot of more students will apply to Columbia. Yes?
Are you just considering one school investing, or there are all the schools investing?
So this is all the schools investing, but like I want to do equilibrium, so I'm considering one school deciding on its first order condition, given that the other schools are fixed. And this indirect effect actually can sort of like be negative, because it's actually bad for you that more students apply to you instead of other schools. If you don't really like those students, they don't help you much, very close to a threshold. But in the other schools, they would make the other school more restrictive and more competitive, and let other students that you do like to lead to you. So one interpretation of the paper by Hatfield et al. Is that when the market is thick, we can actually ignore this. When the market is small, when we have two colleges, this can actually be negative, and schools can have negative incentives to invest, actually. And in any case, you can also look at what is your incentive to invest, targeting different students. And it may, ex post, not seem terribly surprising, but you can show that you want to invest only in things that are attractive to the top students. and you have very little reason to invest for the marginal students. If you have a student that is close to a threshold, probably the students who really need investment in good schools, the competition for the top students will not create any incentives for the school to invest in those marginal students. No? So, yes?
That result somehow depends on the correlation and preferences of schools.
So it's in those expressions too. It's
But if they are not correlated, then in one situation, and when they are highly correlated,
that depends on that too, and it's all in those shorthands that sort of capture this. I'm not going to go into those, but it's in the paper if you want. Yeah. The other application is applications say thinking about random economies. So Attila spoke on Monday about single tie-breaking, multiple tie-breaking. In many situations, we have actually indifferences, and the way that we resolve them is that the schools flip a coin or drew random numbers to break indifferences. So when you break indifferences, you get a procedure that involves some randomization in the middle, and this actually makes things quite hard to deal with, because if I need to randomize and then run the third acceptance, I need to simulate things often to look at the distribution. But if I have a large number of random draws, then I can use sort of a version of the central limit theorem and just look at the limit distribution. So another, I can refer again to the example that I had before. The way that I actually generated the example with the dots is that we randomly drew students from a uniform distribution. So it wasn't any kind of economy was possible. It was possible that everybody would fall on the diagonal, for example, but it's very unlikely. When I draw a lot of points for the uniform distribution, I get some empirical distribution that is very close to the uniform. And basically, I can do this. I can take an economy that is randomly drawn, and what we can show is that the economy that is randomly drawn, if it's large enough, will look like the continuum economy, where you actually have students according to the distribution. And the stable matching will also correspond to the same stable matching of the continuum. So, take a continuum economy defined by taking some distribution of our students, let's say a uniform distribution. I randomly draw your score for each one of the colleges. And suppose that this satisfies this unique market clearing cutoff condition and a couple of technical conditions. And let us think what happens if we take an economy that is not the actual distribution. What we'll actually do in practice is to draw from this distribution. So in single tie-breaking or multiple tie-breaking, we take lottery draws and create an actual economy that is finite, created by draws from this distribution. Yes?
How about student preferences? Are they also uniform distributed?
Yeah, in the example that I did, yes, but you can decide on whatever distribution that you want. So you can decide students who prefer school 1 over school 2 have a score that is drawn from this distribution. Students who prefer yeah.
The number of students that prefer different schools, they are equal distributed? Or
So it's however you like. You just decide on the distribution on the joint. Yeah? So I have this distribution over the joint, the entire student types, and I just draw students independently from this distribution. This generates a randomly drawn finite economy, and let the capacities just be the proportional capacities for this size of economy. So if I had 1,000 students and I want to have a quarter capacity for a quarter of the number of students, then I get 250. Or translating back and forth from the discrete version of the example that I had to the continuum version and vice versa. And now we can look at the random resulting stable matchings. So the procedure is I have my distribution, I randomly draw students, and then I calculate the stable matching. I want to say, what will the stable matching be like? And the answer is, well, look at the continuum version. It will give you a pretty good approximation. So here's the proposition. We get a pretty fast convergence where the stable matching actually converge to the continuum. So let me actually show you this graph. So we did that. We drew students where we said that your score for school C for student I is equal to some epsilon that depends only on I plus some epsilon that depends both on I and C, and gave both of them weight half. So let's generate an economy where your score at college C is half your sort of overall quality at all the schools. This is going to be uniform 0, 1. And half of it will be a quality that is drawn independently for each college. So some economy where there's some correlation in preferences between the different colleges, but preferences are not fully correlated, and I don't know, we just decided on this parametric assumptions for being something that's mildly reasonable as an example. And then what we did is take a draw from this distribution, taking different number of students. So we always had twice as many students as we had seats, and we either had 10 colleges, 100 colleges, or 500 colleges, and either 5 seats per college, 10 seats per college, or increasing number of seats per college. So as you go to the right, there's a bigger and bigger economy in the sense that there's a larger number of students, same number of colleges, but each college accepts more students. And all of those correspond, let's say 10 colleges, all of those correspond to the same continuum economy where half the mass of students can get in. And we calculated what will be the cutoffs for the continuum economy. So for the continuum economy, it was a pretty simple calculation, and it turned out that it's something like 0.7, the cutoffs for all the colleges. Given that we chose something that's symmetric, the cutoffs is the same for all colleges. And then we ask, for each finite market that we draw, how close is the realized cutoff to the continuum cutoff that we calculated, and how much spread is there? So there's 3 lines in each one of those things. Okay? So let me just focus on this for a second. Okay? So the dashed line is what happens if you have a continuum of students, where we take the distribution according to which we drew the students from, calculate the continuum prediction, and this is just gives us the cutoffs. This is just a sort of 3 lines of algebra. Then we take draws for the different numbers for one college, 1 student per college, 5 students per college, and so on. For each one of those, we draw the students. Once we draw the students, we have a discrete economy. We run the Gade-Shapley algorithm on it, and then we look at the score of the marginal student in each one of the colleges, sort of get the cutoffs, the realized cutoffs for this realized economy. And then the blue line here is the average, and the 2 red lines give you the 95% confidence interval. What was the spread of those cutoffs? And you can see that the cutoffs actually converge pretty quickly. Once you have 10 students per college, it's not a huge approximation to just say there's a continuum, not 10. There's a continuum of students in each college. And the realized cutoffs are actually going to be pretty close to the actual cutoffs. And when I say close, here it's close in numerically, between 0 and 1, to say what does it mean for the market to be close. I want to say if I got the continuum prediction, if I said, let me assign all the students according to what the continuum cutoff said instead of what the realized cutoff said, what is the percent of students that I'll misassign relative to what I should really assign in the stable matching. This is the fraction here. So if I have just one student per college, I miss for about 30% of students. I don't do that great. But once I have 10 students per college, I already get less than 50% of students wrong. Once I have 100 students per college, I get less than 5% of them wrong. And this is true whether I have 10 colleges, 100 colleges, or 500 colleges. So this is actually, this comes up to numbers that are sort of close to what happens in New York City. If in New York City you have 500 schools, and each school has 200 seats, you can write the continuum cutoffs and get a pretty good approximation for what the realized cutoff should be. Yeah?
Cutoff is higher when there are more colleges. Do you have any indication for that?
Because of the correlation, because the cutoffs, I think it's because we decided that preferences of the different colleges are correlated.
Does that compete more for the same college when there are more colleges?
So when, no, actually it's not because, sorry, it's not because the correlation. It's because now think of somebody who takes an exam many times. The more times I take the exam, my expected score is higher. Here I have this, it's the opposite of what I said. Here I get this random draw only for 10 colleges.
Right.
Here I get it for 100 colleges. And so it's more likely that for one of them I'll get really high. This biases all the scores of students accepted higher.
But they get higher.
Yeah. Okay. So this convergence actually generalizes a bit of the things that Asaf talked about yesterday. He talked about how probabilistic serial and random serial dictatorship are actually the same. Both of them can be described as a particular example in this continuum model, and part of our result we can show that it follows from this characterization that you can also show that RSD and probabilistic serial converge to each other. And let me switch now to another example showing how to deal with, I don't have time, but let me try to just show you really quickly some other application. So there's so let me just tell you the thing that I'll do now is just show you that we can actually use this framework to solve another kind of problem, like analyzing some more difficult situation to analyze in discrete matching, where you have randomization and on top of it some other mechanisms running around. But using the continuum framework, it actually becomes very tractable. So the question that we start from is that what Attila mentioned is that if you do school choice, there's going to be some inefficiencies when you do tiebreaking. So here's the example for tiebreaking. So suppose that alpha, beta, and gamma are 3 students, and alpha and beta have priority in the 2 schools A and B, but each one of them has priority for the second choice school that he has. And there's some student gamma that doesn't have priority neither at A neither at B. So the way this is an example due to Erdel and Ergin, which basically what they show is this student gamma has no chance of getting into A, because if he can manage to beat alpha for a spot in A, if he gets a random draw, but this will just get alpha to submit to B, where he has priority, reject beta, which then will submit to A. So there's only 2 options here. Either alpha and beta are assigned to the first choice, or alpha and beta are just both assigned to the second choice. So this will create some inefficiency, because half the time, if you randomly break ties, this gamma will actually have a priority higher than this alpha student. So half the time, this alpha and beta will be both assigned to the second choice. So what they suggested in the stable improvement cycle mechanism is that essentially we can improve this, finding a random deferred acceptance with a single tiebreaking, and then running another procedure that will find those situations and solve them. Find that actually alpha and beta here can switch. They don't actually harm stability, because the only reason we made them go to the second choice was because of this gamma student, and that was just tie breaking. And everybody's made better off. Now, ex post, it's a great thing. The question is what happens with incentives in this market. So Attila mentioned that it's not going to be strategy proof anymore, but many things are not strategy proof. The fact that you can only submit you can only submit a rank list of only 12 schools is also not strategy proof. So how worried should we be about this? Well, we would like to be able to analyze an equilibrium. What will happen under equilibrium outcomes if we allow students to switch? And it's actually not easy to calculate equilibrium when you have first everybody needs to strategize. Given what they strategize, you first randomly draw tie breaking and then run deferred acceptance. Solving all of this backwards is a bit complicated, but if you use the continuum framework that we have, it actually turns out to be much simpler to analyze. So let me just show you one example, and I'll go over this quickly because I'm going to be over time, but I want to show you that it's useful. Let's think of an economy, a school district, which has 3 kinds of students: alpha, zeta, and gammas. And alphas and zetas both want to go to the science school. If not, they can go to the art school. And alphas have priority at the art school, zetas do not. Both of them have a mass of 1. And there's a mass of 2 of gamma students who actually only want to go to the art school, but they can misreport their preferences. They can misreport that they will be willing to go to the science school as well. And let's say that the proportion V of them misreports. And now we want to solve an equilibrium. Will they want to misreport or not? So assume that there's a mass 1 of each one of alpha and zeta. There's a capacity 2 at the science school. So both of them can get into the science school. And we want to, and the gammas, there's a mass 2 of them, but only a mass of 1 can get into the art school. So if I solve this, I can solve this using just deferred acceptance with discrete students as well. It will be a bit messy, but in the continuum, it would be pretty easy to solve. Oh, and I need to have some condition on risk preferences of the gammas. So if I want to solve for the continuum, I just say, well, there's a cutoff for the science school, there's a cutoff for the art school. Given the cutoffs, I can calculate what proportion of each one of the masses of students will go to each one of the schools, write 2 equations. which seem kind of long here, but it's actually pretty simple. So the top mass of alpha students that are above the threshold for the science school, 1 minus PS of them, will all go to the science school, will add to the capacity of the science school, the rest will get rejected and go to the art school. And likewise, I can do this calculation for each one of the students given the cutoffs. I just add up all those masses, and then I get that the cutoffs are a simple function of V's, like this parameter that I want to check for equilibrium. So now if I want to check what the equilibrium is, I can see that for any number V, this is going to be the deferred acceptance allocation, and this is going to be the student optimal stable matching. That's what happens when you allow students to trade after deferred acceptance. And basically what happens in equilibrium, now that I have the numbers, I can tell you what happens in equilibrium and show you that actually allowing people to trade makes everybody worse off. Yeah? And the calculations are sort of are pretty simple. The intuition after you do this is actually pretty easy too, because what happens? Under the acceptance single tiebreaking, nobody has any incentives to misreport, because what can the gammas do? They can list that they would like to go to the art school if they're not, but if they end up in the art school, they're worse, they'll become blocking because it's unacceptable. It's better for them to just get unmatched and get to to another regular public school. But if we're allowing people to trade, then what will happen to a gamma student which ends up at a science school? Then there's going to be some alpha students. So let me do this. So if we look at the deferred acceptance, when there's some proportion V of the gammas that apply to the science school, those students who apply to the science school reject both some of the alphas and some of the zetas that go to the science school. So the rejected zetas just become unmatched because they don't have priority anywhere and they don't want to go anywhere else. But the alpha students that you reject actually go to the school that you like. And now you have somebody to trade with. But the proportion of alpha students that get rejected and go to the art school is only half of the proportion of the seats that the gamma student take in the art school. So you get that the students actually like going to the science school because they can trade it away. There's half a chance that you'll be able to trade off a seat in the science school for a seat in the school that you really like. Ex ante, you're willing to take the chances. Ex post, it means that you have some probability of getting stuck into the science school, which makes you worse off, because it's just an arms race to get into the art school. Still, the total number of students who get into the art school is constant. So the gammas in aggregate don't benefit from this. But some of them get stuck in the science school, and it's not only bad for them to get stuck there, but it also rejects some other students who actually wanted to be there. So everybody's made worse off. And only the alphas is indifferent. So in aggregate, everybody is worse off in this economy. And this, I guess I wasn't clear going over it quickly, but it's actually very simple to solve. And especially compared to the fact that if you wanted to do this with discrete stable matching and do the randomization, you'll have I did this in that version as well. It's kind of painful. You have to go through all the different cases and calculate things. In the continuum version, you just write a few equations and you get very nice insight very quickly. So I guess I'll stop here. Maybe I have a summary slide on the other thing. Yeah, so I have a summary slide here. So I guess I should stop here. And like what I would like this to be is like something that's hopefully useful for if you want to just catch some problem and you want to get some intuition for something. Then there's a lot of sort of technical details in like the continuum setup and all of this. But once you get through this, it's actually very simple to write down examples and calculate things. And then you can play around with the intuition a lot. So I hope it will be a useful tool for you guys. Yeah. Okay. So yeah. So thank you. Yeah. Oh. So should so I want to say thank you as well, like being the last speaker. So first, thank you all of you people, all of you for coming to the summer school, and thank you especially to sort of Al, Eric, Scott, and Eyal for organizing this, and of course to Cantu for being here. And I should say, like Eyal mentioned yesterday, but the summer school is in a way the reason that I'm here, because that's the first place I met Al about a decade ago. And he gave me sort of a hint that like there's multiple programs that I can apply to, which lead to this room. And like I think this advice led me here. So I'm only here because of the summer school. So thank you all.
Let me also thank Eric and Al for running year after year a great summer school. First of all, remember that design is a noun as well as a verb. Markets have designs, and one of the things we're talking about here is as you look at the world, as you look at all these human artifacts that are markets, remember that they have designs, they have rules, and sometimes those rules work well, and sometimes they work badly, and it's our job collectively to think about how to fix them when they're broken. And if you're a game theorist, if you're a market designer, rules are data. When you study markets, there was a time when economists studied markets as the supply and the demand. But what we do here is study markets as a set of rules that achieve some outcome. And if you're a game theorist, knowing the rules of the markets through which you interact are valuable things. So when you study markets, think about them as designers. Think about their design, and design as a noun might lead to design as a verb. You might think of ways to design these markets better. So years ago, I was asked to write an essay, one of a series of essays that was published in the centennial version, the 100th anniversary version of the Economic Journal. And the last sentence of my article was this one. It said, "Just as chemical engineers are called upon not merely to understand the principles which govern chemical plants, but to design them, and just as physicians aim not merely to understand the biological causes of disease, but their treatment and prevention, a measure of the success of microeconomics," this was a prediction about the future 100 years, "will be the extent to which it becomes the source of practical advice, solidly grounded in well-tested theory, on designing the institutions through which we interact with one another." So you all make me very optimistic that economics is going to move on to this economic engineering stage, and I'm very pleased to have met you. Thank you. As we mentioned at the beginning, one preliminary sign of this success is that the Journal of Economic Literature now classifies market design as a field, D47, and Scott and his colleagues have created a bunch of D47 buttons for those of you who want to go out into the world as market designers. So you can get them at the door.
We're probably short on supply because there were fewer, we weren't told the number of people in this other school, and so there ended up being fewer than the total students, so we waited less than. Yeah, so hang on. Maybe not all the people showed somewhere.
So maybe we can find out.